Tigadan 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 pam pam tigadan 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 pam pam tigadan 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 pam pam tigadan.
Next presentation comes from Juan Pablo Dorsch, software engineer at the Swiss National Supercomputing Center. He'll be presenting an API that supports and enhances the development of scientific portals that allow web developers and HPC users to adapt their workflows on a more flexible, secure, and standardized way. In this talk, Juan's going to present FirecREST. Juan, how are you today?
Hi, Ryan. Thank you for your presentation and thank you for inviting me. I will share my screen. Let me just check there. Okay, and you see the screen, right?
I can.
Cool, thank you. So,
excellent. Thank you.
As you say, we are going to present FireREST with this RESTful HPC. This is how we call it. It's a project from CSCS. It has already more than 3 years being developing. What we're going to do in this talk is basically explain an overview of FireREST, infrastructure and the architecture of this piece of software, what the API actually can do, the features of the API, and then some examples, some real-world use case for FireREST. So first, a brief overview and explanation of what FireREST is. FireREST is an API. It's an API for web applications that connects a web developer and web development with an HPC center. You say there that resources under development at CSCS, but it can be installed in any HPC center. The idea of the REST API is to provide an abstraction layer between a web development or a web client and HPC resource. And that allows you to give you some standard communication with HTTP protocol. So now when you want to submit a job or list files in your file system, in your supercomputer, you can use now a HTTP protocol. And you will send an HTTP request and you will receive HTTP responses, HTTP status code. So it standardizes the development of applications to use HPC resources. The idea is to create scientific platforms, as you say there. So this is a way to approach scientific people, that's scientific and researchers, of course, from the research institutes and universities to the workflows in HPC centers without knowing the whole spectrum of HPC functionalities like SSH or resource management and such. So I will explain now how FireREST is interconnected with the infrastructure we already have on CSCS and with other tools that we have added to the functionalities on this API. So the idea is this one. You have a user in your research institute or your university, and you want to communicate through a scientific portal to execute jobs, to transfer data, list files, or whatever you want to do in a supercomputer. And in order to do that, you connect with FireREST. So you can see that the blue part is the client side, the user side. And then you see the yellow side, which is basically an HPC center. And you can see that FireREST is the layer that interconnects the scientific portal with the, sorry, there was a question or something? Sorry. Okay, I continue. So you can interconnect your scientific portal with your HPC center through an REST API, which is FireREST, which is the interface between those. So this is pretty simple. You can see that it's pretty much what you want. You submit something with an HTTP request. Somehow FireREST will execute a command on a supercomputer and will return you the JSON of the response. That's the general idea. Now, it doesn't work so easy like that because we need to, for instance, try to touch some part of the infrastructure to basically make it work. Like, for instance, how do you authenticate with FireREST? And the idea was trying to solve this with parts of infrastructure that we already have on CSS, like an OIDC server. And we have the Keycloak server, and we use Keycloak to basically get an access token from the application to access FireREST with that access token. So for the user, this is transparent. He doesn't have to have an SSH key or provide a user and a password for the SSH user in Dane. It just uses a connection to authenticate with the portal, and then the portal will transparently provide the access token to be used with FireREST and to provide the execution of the code. Now, how are these commands executed? Because you might think, I sent a token, and for some point, the command is executed in a supercomputer like Dane, for instance. Well, we manage that with a delegation, which is basically a translation with an access token to an SSH credential or a credential for an HPC system. This credential has some limitations, like for instance, brief duration, and is attached to a specific command and parameters. But the idea is that we create this on behalf of the user, and so there's no sudo or root execution done. We also can see that we have another part of infrastructure in CSCS that are taking advantage here in FireREST. For instance, we use the OpenStack object storage, which is Swift, as a staging area for the large data transfer between a scientific portal and Dane and backwards. Also, this is important because it's really interesting that not only Swift technology is supported by FireREST, but also Amazon S3 is supported. So if you in your HPC center have a different object storage like S3, you can use also FireREST to do this performing these data transfers. Now, another important thing is in the infrastructure of FireREST is the gateway. We use the gateway to basically redirect all the incoming requests to the specific microservice. Because I didn't say this because I don't want to really go really deeper on this, but FireREST is a microservice architecture. This is really interesting because it basically helps us to provide redundancy in microservices. They are lightweight, so we can basically set it up really fast, all the microservices. And the idea is that the gateway connects an HTTP request to the specific microservice. It also provides the checking of the OIDC signature, because maybe you can connect FireREST with another OIDC token, but if it's not signed by the certificate, by the OIDC server that issued the token, then it won't be able to enter FireREST. We also provide in the gateway rate limiting, load balancing, and logging, because we logged everything on FireREST. And you can see that the whole picture of all of this is something like this. So you see that we touch a lot of infrastructure. I didn't even talk about the internal infrastructure because, well, I think that we can see that it's pretty complicated, everything there. But we touch a lot of infrastructure, and that was an interesting job to already take advantage of what we already have on CSCS. As you can see also, something that you mentioned is that we log everything to our Elasticsearch log server, even the commands that are executed on Dane through FireREST. So we control everything. We can provide traceability to probably all the problems that we might have if something comes wrong in FireREST. So this is the infrastructure, and you might think, okay, let's go now to what actually FireREST does. So let's talk about the API. So with FireREST, we provide, as I said before, HTTP requests, basically to interconnect with an HPC resource in an HPC center. So you can see now that we have a method is like get. We would have another verbs, HTTP verbs like post, like delete. We have a microservice like a status, and then we have the operations on those We have the utilities microservice to perform small and low latency operations on the file system, like listing a directory or renaming a file or making a directory. Of course, we have the compute microservice that is one of the most important because it's the one used to submit a job, to get information from one job or a list of jobs, and to delete a job. And you see that we use the verb delete, not cancel, like for instance in a resource manager like Slurm, because basically the idea is to abstract the idea that we have a resource manager behind FireREST. FireREST will help you to use these verbs and this endpoint as an HTTP request. So now delete will be deleting or canceling a Slurm job or another job, like for instance a job with I don't know, OGE or Dorsch now. We also have the storage microservice that is used to large data transfers within the file systems, moving one file or directory between file systems in the same HPC center, or to do a download or upload from outside the SES. So we show you how is FireREST inside, what FireREST can do. Now let's try to pass to a real world example. So because everything is really easy right now, you can see that everything is really nice. But let's see how this actually works, right? So first of all, let's start with this SELVEDAS project. What is SELVEDAS project? SELVEDAS stands for Service for Large Scale Volume Experiment Data Analysis. It's a project collaboration started by SUSE University between the Paul Scherrer Institute, PSI, and CSES. So what does PSI have? They have the Swiss light source, which is basically a synchrotron light source. It's a reflection light created by, as I remember, created by an electron moving something like the light velocity or near to the light of velocity of light, and moving through a magnetic field. It basically provides an infrared spectrum range, which allows you to study an object. You put the object in this Swiss light source machinery, and you will have information, really, really high resolution information of a lot of properties of materials to be used in pharmaceutical research, in storage technology, and some other in energy and some other applications that you can see there in the list. So these are the kind of things that the SLS can provide. You have an object like here in the left, and this is the kind of images you will get. Okay? Images are discretized, of course, like pixels. And the idea for the researchers that use this SLS in PSI is to get information of region of interest of the experiment, like this kind of results that they would like to see in the output of the experiment. So what PSI has before SELVEDAS, let's say, is this kind of workflow. So they have, I will explain the psychography 3D, which is a high resolution tomography that offers results of scanning areas of 100 nanometers, as you can see there. And what PSI does, or did before SELVEDAS, let's say, is they use what they call the beamline, which is a cube, because they have to wait a long time to use this kind of technology. They submit their job or their object in the beamline. They wait for the time. They have this window time to use it, and then they needed to analyze the results of the psychography into an HPC system. Now, this experiment, this calculation in the HPC system needs to be really fast because they have few times in the beamline to use it again when they have to feed back this information to the psychography again to get more information about the a region of interest. Doing this fast typography reconstruction is really expensive in time and resources. So what PSI needed was a supercomputer. And who has a supercomputer? Well, CSCS. So the idea of SELVEDAS is to provide the workflow interconnection between the data generated by the typography or other SLS technologies, sending to storage in CSCS, analyze, and coming back again to, as I said before, study the region of interest. Now, SELVEDAS wants to provide a web portal, a web client in PSI side to connect to CSCS. And how can they do that? Well, they thought, of course, of FireREST. If we have the API and they have the idea of a web client, they have to connect the web client to FireREST, which will connect to CSCS. So now you can see that this is the idea, the general idea of the SELVEDAS project. You can see, I will come back to this image, that the HPC system that they had on PSI now has been replaced by DAIS, and they will use FireREST as an interface from the web portal. As an analogy of the first images I show you, the blue part, the client part is PSI, which basically uses this PSI portal to have a location time on the beamline. And when they have the time, they will send the object to the typography. They will receive the first result, and then for studying these results, they will send the data to be analyzed in CSCS through FireREST. And then they will reserve the return, the area of interest of the fast feedback experiment. So this looks pretty easy to do, but of course the workflow, the high-level workflow is a little more complicated. So what we did, and this I will repeat this again, this is a high-level solution of the workflow. What we did on SELVEDAS was decouple the problem in steps. First of all, the first step, all the steps are related to FireREST calls, of course. So the PSI portal will be programmed in a way that these steps are delivered sequentially. Like for instance, if you see the first point, which is the setup of the problem on CSCS, is basically creating a directory where all the files from PSI will be moved or copied to CSCS storage. The second point is actually calling the external transfer API endpoint, here the upload, from moving the local file in PSI to a target path in DAIS, as you can see here. So you can see there that basically if you use a curl and a -x in this kind of commands, you will have an API call that they are actually using in PSI side to use FireREST. So once the data is moved or copied to the storage in CSCS, they need to do the calculation. So they activate the compute microservice or the compute API to upload the netbatch file, which have the orders to, of course, execute the calculations needed on DAIS. Then, when the calculation is over, they will need to restore the data, or take the data to the portal for the scientists to be analyzed and to do, again, as I said before, the feedback experiment. In order to do that, they have to download the file or the object. Internally, what FireREST does is moving the data to the staging area and generates a temporary URL to be downloaded by PSI. And actually, this is working. This is a really good use case that we have right now. And yeah, this is one of the first real world experiments we have with SELVEDAS. So I don't have right now captures or a video of the PSI portal. I would like to show you, but you know, there's some confidential things between PSI and CSCS. So I will show you a demo web client that we have arranged to see how FireREST can be used and how FireREST can help to people to get more information in a better way, in a UI way, of some resources and workflows done in an HPC center like CSCS. So I will show you this video here. I think that you might be seeing the window of the video. So we record this demo. So we have, first of all, you can see here that we are entering our CSCS account because we are using, of course, OIDC, as I said before, or Keycloak. So we can see here the UI. You can see here the username of the person that is executing and where it's executing. Now we are going to set a job with a number of nodes and steps, the name of the job, the partition that will be used, and the constraints. This matches partitions and constraints in Paint, of course. And when the job is submitted, you can see all the steps will be executed. You will have a long time waiting for this because, of course, we have 30 steps to be executed together. And you will see that the jobs are being executed right now on the queue. You can see all of this in a UI in a way that is clearer for whoever that wants to actually be seeing a workflow, a real workflow on HPC resource center like CSCS. You can see this is the native call to the compute API when we submit the jobs and we list, the jobs. You can see here that this is a JSON response, which is what we want actually. And this JSON response is, as you can see here, all the information from the pending jobs and the time that it's been running. All this information is parsed here in this table really easily because it all manages HTTP request and response. At the same time, you can see that the files, this is the work directory that was created automatically. And you can see here the files that are being updating with the steps and the solutions of the problem. This is a PFR problem. This is an example of the problem that we are just running for demo. Now, if you can start the post-processing, this will start a new job. And this job is going to do the post-processing. You can see there that the post-processing job is running on the normal partition. This is live queue of the directories, live queue of the job. And you can see that when the post-processing job finishes, you will see automatically how the image of the result is being created. This is just an animated GIF that is downloaded with FireREST from the results. From the result, you can see here the result image that is being loaded in the same result directory live in this queue with FireREST. And well, I will leave you here some information about FireREST. You have the GitHub repo, which is a public repo, the documentation in Read the Docs. And we also have a Python client for FireREST. So it manages really, actually the client that we saw just right now was developed with this Python client. And this easiness, the development of clients using FireREST with this Python module that is already available, publicly available on pip also. So you go to pip and put FireREST and you will receive this client. So now I will leave you with questions and comments.
Thank you, Juan Pablo. So Hussein, I know you have a question.
Yes. Actually, I have two questions for you, Juan. The first one has to do with the storage. You mentioned two storage solutions that supported. One is Swift, that's related to OpenStack, and one was S3.
Yeah.
I'm wondering, are we talking here about the standards of object storage? So if we take Ceph, let's instance, any solution that talks object storage could be used in this case, or here, because we have this resource at CSCS, we had to make that working with these two solutions mentioned.
Well, first of all, we've been thinking on the solution that we already have on CSCS, that was Swift. Then we saw that the same Swift object storage in CSCS has this interface with S3, so we think that it might be good to add this abstraction layer also for S3. And we can work, we're looking at the technologies right now, but since S3, I think, is one of the most expanded, we just went with S3 and Swift. But the abstraction layer is pretty, I think it's pretty easy to customize to another storage technology like Ceph, for instance.
Okay, so this is the first one. The second one has to do with, thank you. I mean, that's perfectly fine. That answers my question. Second one has to do with the advantage. I mean, if we think about it, the FireREST itself, yes, give us an advantage from some automation point of view. I mean, the easy of the web, it's cloud-oriented way for dealing with running jobs. Is there any advantage at the level of, let's say, reducing some kind of workload to avoid repeating some kind of work? For instance, for the serverless kind of workload or others?
Yeah, I mean, the idea is to automatize all the workflows. So FireREST gives you the possibility of automatize your workflow, but at the same time to provide different kind of workflow for different tasks. So it will depend, of course, of how you manage the REST API. This is more like part of the developer, the client developer that will use FireREST side. We manage, the REST API is as it says, it's just responsive, it's restless. It doesn't have states for a lot of things. It's to just submit something, to submit a request, and you will receive a response.
Yep.
I think it is more in the client side that to manage how to manage the workflow of the scientific workflow, actually.
Yeah, remove some complexity there too, and that's straightforward. That's a big advantage. Yeah. Thank you very much.
To you.
Ryan.
All right, Juan Pablo, I don't have any other questions right now in the queue, but I'll send them to you if they come in the coming hours.
Well, thank you. You have
Bum 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 bum